In this video, we're going to be talking about compound probability. That's basically the probability of two or more events occurring, and we can calculate the compound probability of both independent and dependent events. So first, let's look at a real-world example of an independent or two independent events. My example here is that when we flip two coins, they are independent of one another. That means basically each flip does not have an impact on what happens with the other coin flip. The formula for finding the compound probability of independent events is the probability of events A and B happening. Remember, this is our symbol for and, or the intersection of those two sets, is the probability of A times the probability of B. So remember, we are going to be multiplying here. If we were looking at dependent events, though, that would be like when you pick a card from a deck, you don't replace it, you don't put it back in the deck, and then you pick another card, okay? Now you're decreasing the number of cards in the deck. You are impacting, the first event is impacting the second. The formula for this starts off the same. It still starts off probability of A and B occurring is the probability of A times, so we're still going to multiply. But what we're changing over here is that it's the probability of B after A. So this means we have to take into account how the probability has been altered by event A already occurring. Let's look at some examples so you can understand that a little bit better. All right, for number one, suppose you roll a die and you flip a coin at the same time. What is the probability you roll a 2 and the coin lands on heads? First, let's start off by establishing that these are independent events. So rolling a die and flipping a coin does not have an impact on one another. So let's say that we want the probability of getting a 2 and then landing on heads. Well, the probability of rolling a die and getting a 2 is 1 out of 6. The probability of flipping a coin and getting heads is 1 out of 2. And we're just going to multiply these together, so our total compound probability here would be 1 over 12. Number two, suppose you have a standard deck of 52 playing cards. You draw a card, replace it, and then draw a card again. What is the probability that both cards are spades? So we want basically the probability of a spade and another spade. And when we're doing probabilities of a deck of cards, or you're going to see ones with like a bag of marbles or a bag of objects, we want to pay attention to, are we replacing the item or not replacing it? We are replacing it here. So we start off with 52 cards, we pick one, and we put it back. That means we get 52 again. So in a deck of cards, there are 13 spades. And once I put that card back, we're going to have 13 spades again. So 13 over 52 times 13 over 52. You could have also reduced that. So 1/4 of a deck of cards is spades. So you could use that reduced fraction. And I'm going to use that one to multiply here. And I'm going to get 1 over 16 as my compound probability. Number three, a coin is flipped and the spinner below is spun. What is the probability the coin lands on tails and the spinner lands on an even number? These are independent events again. A coin flipping and a spinner being spun does not have any impact on one another. So we're looking for it to land on tails and then an even number. So the odds of a coin landing on tails is 1 over 2. In this problem, the odds of the spinner landing on an even number is 4 over 8. But if you want, you could also use the reduced version of that and say, well, half those values are even, so 1/2 times 1/2, and we'll get our compound probability to be 1/4. Okay, number four, a card is drawn from a standard deck of playing cards. It's not replaced, and then a second card is drawn. What's the probability the first card is a diamond, and the second card is a club? All right, so let's take a look at this here. So we're looking for the probability that we have a diamond and that the second card is a club. So in your standard deck of cards, there are 13 cards that are diamonds. There's 13 cards that are clubs as well. However, since we have now drawn a card and we're not replacing it, this denominator is not 52 anymore, it's 51 because there are only 51 cards remaining in the deck. This is our first example of looking at the probability of dependent events because that second probability is now impacted by that first selection of a diamond card. You could have also chosen to do this as 1/4 times 13 over 51. And I'm going to multiply those fractions in my calculator. So 1/4 times 13 over 51. And let's put that back as a fraction. And I get 13 over 204 as my probability. Number 5, a number from 3 to 10 is chosen at random, and then a die is rolled. What's the probability that a prime number is chosen and the die lands on a number greater than 4? All right, so let's talk about this here. These are independent events. They're not impacting one another. If I'm looking at numbers from 3 to 10, I'm just going to jot them down for a second so we could look at it. You can see that we have 8 numbers here. How many of them are prime? Well, 3 is a prime number, 5, and 7. So the probability of a prime number and then a number greater than 4 on the die. Prime number is going to be 3 out of 8. On a die, there are 2 numbers greater than 4, right? 5 and 6, so 2 over 6. Or you could have chosen to do 3/8 times 1/3. Either way, we're going to get 3 over 24 or 1/8 as our compound probability. Number 6, a bag contains 26 pieces of paper, each with a different letter of the alphabet written on it. If a paper is drawn at random, replaced, and then a second paper is drawn, what is the probability that both papers contain letters from the word math? All right, so we want a letter from the word math. Okay, so letter from math. And I'll put here, we also want a second letter from math. Well, the word math has 4 unique letters, so the probability of selecting M, A, T, or H is 4 over 26. And since we were replacing the letter or that piece of paper, we are still going to get 4 over 26 as our second probability. That makes these events independent of one another. If we work with the reduced versions, this is 2 over 13 times 2 over 13. And we get our probability to be 4 over 169. Number 7, Ian has a box of 25 munchkins and is about to choose one at random to eat. There are 8 chocolate munchkins, 10 jelly, and 7 glazed. What's the probability that the first munchkin he takes out is jelly? He doesn't replace it. Remember, that's key. And the second munchkin is chocolate. Okay, so we want probability of getting jelly and then chocolate. Well, the probability of jelly when we first start off is going to be 10 out of 25. There are 10 jelly munchkins and 25 total. Then we want to pick a chocolate one, so that's going to be 8, but it's going to be 8 over 24 because we have taken a munchkin out and we have not replaced it. We're going to simplify these. 10 over 25 is 2 over 5. 8 over 24 is 1/3. You could use your calculator as well to simplify. And I'm going to get 2 over 15 as my answer for 7. All right, for our last question, a bag contains 16 marbles. There's 3 red, 7 green, and 6 blue. 2 marbles are drawn at random without replacement, so these are dependent events now. What's the probability the first is red and the second is green? All right, the probability of selecting a red marble is 3 out of 16. We're not going to put that marble back, so now we only have 15 to choose from, and we want it to be a green one, so 7 over 15. And now let's just simplify this. So I'm going to use my calculator to do so. So I have 3 over 16 times 7 over 15. And I'm going to put that back as a fraction, and I get 7 over 80 as my probability for number 8. You can check out other videos in this playlist to learn more about probability. Thanks for watching.